I'm not going to tell you about the next generation. I'm just assuming you are the next generation. I'm just going to tell you what I think. Okay, so as Lars said, my name is Michael Tiller. Thank you all for coming. So a little bit about who I am. So I'll try and be quick here. So I started my career at Ford Motor Company working on powertrain research. And I worked on one of the, not one of, the original Ford Hybrid Escape. So for those of you who don't know, the Ford Hybrid Escape was the first production hybrid in North America. It was second only in the world to the Prius, which was produced in Japan, obviously. It was the first hybrid SUV. So it was a lot of fun, and I used Modelica a lot on that project. In the meantime, I've done various things. I've been a consultant and an entrepreneur for various companies. You can see listed there. I'm currently the CTO at a company called Realis Simulation, which used to be a business unit inside of Ricardo, for anybody who knows who Ricardo is. I'm the author of 2 books on physical modeling, and I programmed in pretty much every language from 6502 assembly to Zig over my career. So even though a lot of my work is in engineering, I've always just been really passionate about software engineering. So I should say, since most of my career has been in mechanical engineering, but I've been passionate pretty much my whole life about software engineering. I noticed looking at the people in this audience and the people at this conference, there's a little bit of a generational gap between me and most of you. My observations are that, the average Julia user probably has their first computer is probably an Apple MacBook, and their first IDE might have been, VS Code. First scientific language may very well be Julia. When you think of assembly language, you probably think of something like LLVM. And a popular song from your youth would be something like Fast Car. So for me, first computer was an Apple IIe. My first IDE was punch cards, probably. My first scientific language was in Fortran. And when I think of assembly language, I think of 6502 assembly. But interestingly, we have this in common. There was a popular song in my youth also called Fast Car. So, okay, so I'm just acknowledging this sort of generational gap, right? Because I know what all of you are thinking. But I'll do my best to tell you something you think is of value here. In fact, I'm reminded of this scene from Real Genius. If you haven't seen it, I don't know if you'll be able to hear it here. No, you can't hear it because my sound's off. Anyway, I'll skip that. But anyway, okay. So just a couple quick words about Modelica. As was mentioned, I'm a member of the Modelica design group. I've been involved in Modelica since about 1999. I'm currently the secretary of the Modelica Association. I'm the president of the North American Modelica Users Group. I'm the creator of the Modelica Playground. I'll quickly show what that is. I'm the author of 2 books. One is Introduction to Physical Modeling with Modelica, which is only available in a sort of dead tree format. But Modelica by Example is available online. And so I can just sort of quickly show you a couple of things here. So it's not, okay. So Modelica by Example, as I mentioned, is an online book. You can find it pretty easily. It features some interactivity. So all the examples in the book, you can simulate online. So you can change values and play around with them and resimulate them and so on. So, and then Modelica Playground is a place where you can create Modelica models. This is the sort of classic model in Modelica of a bouncing ball and how you would model that. And then you can simulate it, and it allows you to generate reports that include things like animation, so you can see things like the bouncing ball and the plot of the trajectory of the bouncing ball. So anyway, so I'm the creator of those as well. Let me pause this so it doesn't slow my computer down while I'm doing this presentation. So okay, this is just a quick taste of Modelica for people who haven't seen it before. So you have the ability to define connectors here. The connector has a voltage and a current associated with it. Then you can create components like a resistor that have these electrical connectors on them, P and N, and then you can write out equations associated with the resistor, most specifically Ohm's law and the conservation of current. And then you can combine those components into essentially system models. So you can have an RLC circuit here. You connect things up, and you can compose these into very deep hierarchies. So you can start with a car that's composed of an engine, a transmission, and a driveline, and then the transmission might be composed of gears, and it might have a hydraulic aspect, which has valves, and all the way down. So I've even way back when I first started working with Modelica, we managed to create a model that had about 250,000 equations in it using this kind of compositional technique, building up complex models from hierarchies. But I just wanted to give you a sense of the flavor of the language. It's a declarative language. It's not an imperative language, is a key thing about it. So you're thinking Modelica, you know, why, this is JuliaCon, right? So why is this guy going on and on about Modelica? By the way, does anybody know what this meme is in reference to? All right, very good. All right, excellent. We're all the same generation. Okay, so this is not a talk about Modelica, but I just feel like I have to give some context here. So the first thing is I come in peace. So one of the reviewers to my talk made this comment like, okay, he seems like he's, you know, he said he seems like he's coming in peace. So, okay, yes, I am. I'm not here to criticize or to try and convert you to Modelica. That's not the purpose here. I will say that, I mean, out of respect to a lot of my colleagues in the Modelica community, Modelica is a very solid, very stable technology. But the thing I'm asking myself is really what comes next after that, right? I mean, it's stabilized. So, I mean, it's good. It's good at what it does. But the thing is, you know, innovation being what it is, something's going to come along and disrupt it, right? So the thing I want you to understand is I want you to innovate. I want you to disrupt, all right? I want to see the modeling and simulation space improving and more new technologies and more capabilities, okay? So that is part of my motive here. But the thing I will say is the Modelica design group was full of some really, really smart people, and they gave a lot of thought to what's going into Modelica. And I just want to make sure that the next generation of people look at it and understand that there's a lot of value in there. In fact, you know, we spend a lot of time on these detailed discussions. It's hard to know what's going to be important and what isn't, but Modelica has, you know, 25 years under its belt, and I think we've figured out what, you know, what was important in those 25 years. But, you know, sometimes we guessed wrong, sometimes we guessed right. But that's also hard-won knowledge that, you know, the next generation can take advantage of. And you know, in some cases we sort of guessed right, but then, you know, technology changed out from underneath us. I'll talk a little bit about that. So the other thing I'll point out about Modelica is that there's an extensive standard library across many, many domains. And there's a lot of content, a lot of, again, hard-won knowledge in there. And just be aware of it. It exists. There's no reason you can't learn from that directly. So, okay, so back to the Julia community, right? So also full of very smart people, okay? Doing some really amazing work in the area of modeling and simulation. I'm very excited about what's actually going on in the Julia community. So there's been, in fact, even several notable cross collaborations between the Modelica community and the Julia community. Modia is this effort by Hilding Ungfist and Martin Otter, who were two of the, you know, main people in the Modelica effort. There's ModelingToolkit by Chris, you know, there's some mixing of Modelica ideas in there. What's that? Yingbo, yes, and Yingbo. And then there's openmodelica.jl, which is a sort of a collaboration between the Open Modelica group to work in Julia. And, you know, of course, you're going to be trying to figure out what's important and what isn't important, just like we were. So, you know, you certainly should try and, you know, follow whatever your intuitions are. But I'm just trying to give you a way of maybe avoiding rehashing things that I think are pretty clear cut that we had to go through as well. So I'm going to go through a couple things here, you know, things I've learned along the way. So one thing I noticed, I mentioned I work for Ford, and it's been very frustrating for me through my engineering career because I've always faced, and when I use the term engineer in this context, I'm going to be talking about like mechanical engineers, electrical engineers, and so on, okay? It's a little ambiguous, but that's just my habit. So dealing with engineers in those kinds of industrial settings, they have a difference of opinion about this. They think that what they're doing, this modeling effort that they're doing, is not really like software development. And this is something that just gets under, it kind of annoys me. Because the thing is, from my perspective, modeling is really just a special kind of software development. And what I mean by that is that modeling benefits from having version control. It benefits from CI/CD processes. It benefits from artifact management. It benefits from unit and integration testing. And it benefits from having a good, fast software development lifecycle. Instead, in the engineering world, they want to have their own tools to do basically these exact same things. And I just don't see why, you know, these are all solved problems. We should just move on from that. Just use the tools that are available. Use Git and use GitHub and use all these other tools, right? So that's just one thing to be aware of if you ever have to interact with engineers in an industrial setting. At the end of the day, simulations are just functions. You know, they have inputs, they have outputs, and you know, they should. One of the things that I find is that they need to be callable from other tools. It's not just enough to be able to just run a simulation, because you have to you have to integrate the simulations into the product development process. And that means that they might become part of some larger process. In fact, they're almost certain to become part of a larger process because nobody just runs one simulation. I always say simulations are like Doritos. Nobody just has one, right? You have to run it multiple times to get anything of value out of it. And so that just reiterates the idea that it's a function that you might want to build up higher order processes on top of that, which are themselves functions, in order to do your analysis. And I'll point out technologies like FMI and EFMI, which if you're not familiar with them, that's not the topic of this talk, but these are things that came out of the Modelica Association to make it so that simulations could effectively be embedded in other things, to treat them as functions for the most part. So, and those standards caught on, very quickly, which just indicates the pent-up demand for that kind of functionality. Another thing I commonly point out is that there's this sort of, in terms of the need for models, there's a sort of continuum in most businesses. There are some people in industry who have an amazing grasp of the physics of the systems that they're working with. They understand these hydraulic valves and how friction works and wet clutches and dry clutches. They understand all that stuff. Now, when I say, but the thing is, so the first thing is you got to give them a way to capture all that knowledge, what they understand about that. Give it not just a way to capture it, but ideally to help take the value that's represented by their knowledge and deliver it to the rest of the organization so that they're not just the gatekeeper who or the oracle who answers questions about this, but they can take that information and deploy it out to the rest of their organization. But also when I say some, I really mean very few. There are some, this is true, but there just aren't nearly enough in most cases. And so you have to keep that in mind. They represent sort of the top of this pyramid, all right, where the rest of the company is underneath it. And so since most people do not have an amazing grasp of physics in these organizations, we need to find a way to reach them. And so that means things like low/no code solutions, developing graphical modeling environments, developing turnkey applications where you just, what I would call a casual user, or maybe that's probably the best term, just enters data or makes a few choices and then pushes a button and gets the results, all right? And so it's important to have tooling that gets to that point, not just that the genius engineer can use, but that everybody in the company is getting value from that. And another thing that I found interesting in the process of developing Modelica was this notion of specifications versus implementations. And what I mean by that is Modelica took a specification-based approach to what they did. What that means is that there were efforts like VHDL, AMS, and so on that were attempting to develop specifications that would be published, and then multiple tool vendors would implement them. And that's the approach that Modelica took as well. And I'm not so sure that's the best idea. A good analogy in the modern day, I would say there's two here, are things like browsers. Now, browsers tried to take a specification-based approach, and I mean, they did take a specification-based approach, and then they quickly aggregated into basically two. So the idea that you can have multiple teams putting in this enormous amount of engineering effort to implement exactly the same functionality, it doesn't scale very well. Ultimately, people will join forces and may ultimately end up with just one in the end, depending on how long Mozilla can hold out in this. But anyway, Python's kind of the counterexample, right? Python is, there's no specification, there's just an implementation. This is just Python, right? You can make CPython and you can make PyPy and you can make other variations of Python and whatever, but really there's just one implementation. Everybody else is using that implementation as a specification. And like I said, Modelica took the approach of doing the specification-based stuff. I'm leaning much more now in my later years in this sort of standard versus /reference implementation kind of approach. I just think it's a better allocation of resources. A couple of miscellaneous things to keep in mind. So, in an industrial setting, the results matter far more than the technology you use to accomplish them. I love technology, so this is something that kind of breaks my heart, but it's really true. Yeah, and so you just have to always keep that in mind. If you want to sway people, it's not going to be by, I can't imagine going to one of my managers at Ford and raving about just-in-time compilation. I mean, he wouldn't care or know what he was talking about. So, so that's one thing. One of the things that I found where I was most successful, I would say, is, I'll use the Ford Hybrid Escape as an example. So Ford at the time had a lot of engine and transmission analysis capabilities. They've been making cars obviously for a long time. And the thing was though, that all of the efforts that they had to analyze powertrains were to validate against dynamometer data. You probably don't even know what a dynamometer is, but it's this thing that you stick the engine on, you palletize the engine, you stick it on there and you run it at sort of constant speed all the time. And then you measure things like the brake specific fuel consumption and other, and torque and whatnot. And then you wanted the models to basically be simulations of those dynamometers because that's what the data was. You had dynamometer data, so in your simulation, you had to simulate the system like it was on a dynamometer. And where this sort of, the comical effect of this is that when the first hybrids came out, hybrid vehicles, one of the things that they do, unlike conventional vehicles, is they shut off all the time. The engine shuts off and turns on, shuts off and turns on. So whereas a conventional vehicle is just idling, right? And that's an important point when you try and figure out the overall fuel economy of a car. The hybrids don't. They shut down and they turn on. And so it turns out that one of the things, there were a bunch of issues, but one of them that I worked on was how do you minimize essentially the vibrations when the engine starts and stops? And none of the analysis tools we had could do that because they were all used to just running the engine at a normal, steady operating condition. They had nothing in them for modeling the dynamics of starting and stopping the engine. Well, it just wasn't something that they cared about. They never did any tests like that. And so this formed a vacuum in terms of Ford's analysis capabilities, and it was easy for us to step into that vacuum, right? They would take anything because they had nothing, right? So even if this is just a nascent technology, you can get in the door there, as opposed to being in a situation where you have a whole bunch of entrenched players and you're trying to displace them. That's much harder. So one suggestion I would have for anybody who's trying to advance any new technology, Julia or otherwise, is to try and find where those vacuums are. Try and look at how innovation is changing that landscape of capabilities, and then find where you can sort of anticipate there's going to be a void, where something's going to be missing, and then try and fill that void. On the modeling side, it's nice to solve differential equations, but at the end of the day, because of that sort of pyramid I showed you before, most people they don't have the knowledge of the physics to build up component libraries that do a good job of accurately reproducing the physical response of systems. So if you can create the content for them, that's a big selling point. Transferring that, basically codifying your knowledge of something into something you can hand off to them is really the way to go. And also, one of the things we did in Modelica, at least, was we handled this notion of refactoring. Let's say you make a model and you give it to a customer, and then you decide, well, you know what? I'm going to refactor this model. I'm going to change the name of this parameter. Or I'm going to add a new parameter, or I'm going to move it to a different part of, give it a different name, something like that. You want the end user to be able to easily upgrade their system to use those, and so we would actually include in our models these refactorings as sort of symbolically or declaratively, saying, oh, from version 3.13 to 3.14, this model changes name to this, or this parameter changes name to this. So that you could, these are often called code mods in the JavaScript world, so that you could actually update downstream code from those changes. So that's just another thing to keep in mind that Modelica did. And you see this, like I said, in the JavaScript world. I'm not sure what it does, what happens in Julia. In terms of machine learning, obviously machine learning is a big topic right now. With a couple of things that I tend to think about when it comes to machine learning. The one is something that Chris talked about in his talks earlier today, which is that if you can use a first principles model, that's really nice. That's the model side of his little beaker with the model and the data. If you can put some model in there, put some model in there. There's no sense in trying to figure that out from empirical data if you know what the structure should be. At the end of the day, neural networks are just regressions, and so just try and keep that in mind. They're not pixie dust. They're not magic properties from alien civilizations. Another thing to keep in mind about simulation data and how it meets machine learning and AI that I try and point out to people is that if you think about something like credit card transactions, you've got, if you take a terabyte of credit card transactions, what you're going to have is about 100 billion credit card transactions with a few columns of data. And you can infer patterns from that kind of data a lot easier than you can from 1 terabyte of simulation data, because it might be a CFD run, it might be one simulation, it might be one case. So there's no way to sort of infer a pattern from from one data point. So the way I usually refer to this is that it has a different aspect ratio. You know, it's heavily weighted on columns and versus rows as opposed to the other way around. And so when we think about applying AI and machine learning to simulation, we just have to kind of keep that in mind. Time series data is a little different because it is kind of moving forward in time, so that's kind of like rows in this thing. But anyway, just something to keep in mind, because I know everybody's got a lot of enthusiasm for these kinds of techniques, but you know, credit card transactions are not simulations. A couple things have changed in this time that are worth noting. I mean, graphics. I would encourage you to be like Modelica in one regard, which is that in Modelica we captured all the graphics associated with the model in the model itself. It moved with the model. It didn't reference some file somewhere that could, you know, where you could have a dead link to the file. Everything, including the documentation, all sort of was embedded in the model. But don't be like Modelica. Don't invent your own vector graphics representation, which is what Modelica did. At the time, we knew about SVG, but it wasn't that well supported. And so everybody was kind of worried about adopting it and then having it sort of not be well supported. But now it's widely supported. And we did lots of things in Modelica to do dynamic diagram rendering and stuff like that. You can do that just as well in SVG if you give it some thought. Another topic is target architectures. So I'm big on the web, as you saw from my two examples I showed you before. I would say don't be like Python. Don't relegate yourself to the server side. There are lots of interesting possibilities to target things like WASM or JavaScript or something so that you can get into the browser as opposed to being removed from the browser. And along those same lines, FMI is another example of a target that you might want for interoperability with other systems. For embedded systems, you have EFMI or hardware-in-the-loop systems. Ideally, you know, these kinds of things where you have a runtime-free option, so you don't have to install Julia in order to use the analysis code. And then there's all kinds of really interesting things going on with containers and serverless and beyond. A lot of it based on WebAssembly. Things like Cloudflare has some really cool worker things that are based on WebAssembly. I call these to your attention just because they're real opportunities to be using Julia, and you don't want to lock yourself out of them. Okay, so why Julia? So I see several opportunities with Julia. One is this fantastic ecosystems that you guys have built, and it's a really great foundation for modeling and simulation. ModelingToolkit, you know, for higher level modeling, you know, just getting above the differential equations and actually being able to compose models in a more declarative way, kind of toward the Modelica effort. One thing I'm really excited about is this idea that you can have more modular tool chains. In Modelica, most of the tools are monolithic. It's GUI all the way down to simulation. There's no point of being able to substitute pieces or being able to branch off. And so the idea that you could have sort of separate GUIs, models, symbolics, targets, simulations, I think that's really interesting. Chris mentioned earlier today ideas about leveraging symbolic transformations for looking at stochastic processes and all kinds of other things. That's also pretty interesting, kind of related to that previous point. There are some what I would call risks and opportunities. They can be opportunities if you make them opportunities, but they're risks, I think, if you ignore them. This sort of Turing completeness of a language is a double-edged sword. Modelica doesn't let you do anything. It's not quite a Turing complete language, and that's deliberate to make it so that the symbolic manipulation doesn't get tied up in knots. So sort of use Turing complete constructs at your peril, I guess, is the thing there. Debugging acausal models, because they have simultaneous systems of equations, is quite hard. And so think about that. Think about how you're going to do that, because if you go down the same route that Modelica did and you don't think about that, then that's going to be what everybody complains about for your modeling capabilities. Low-level error messages for high-level errors are really unhelpful. So if you end up with something that just says, oh, this is a singular Jacobian, people are like, okay, all right, what do I do with that? So you know, think about how you can percolate those errors back up to where they originated and localize them to where they originated. Different domains may require different user interfaces or different file formats. I think the NeuralBlocks one talked about making a DSL. Maybe. I mean, that's something to definitely consider. And I think static typing is important. In Modelica, we have this replaceable construct that's very, very useful for making sure that things are physically compatible, and I wouldn't want to give that up. Anyway, okay, so in conclusion, I'm super excited to see what the developers in the Julia community come up with. There are a lot of good ideas out there, a lot of really interesting use cases that came out of the Modelica effort, and so you might want to try and incorporate some of those. hopefully, you can feel free to read my book about Modelica, if only to try and extract some of the good ideas out of there. Lots of opportunities for the Julia community. And with that, I will open it up for questions. Did I do it, Lars? I think I was right on the dot, I think. Okay, Brad? Well, I can do it here. Yeah, that's part of my warning, is that I'm not sure we came up with a great way of doing that. I mean, it really comes down to, in the acausal systems, people who come from Simulink are used to causal models, and they're used to being able to step through and see where the data got corrupted. But when you have a simultaneous system, everything changes all at once, and it's all wrong. And so you can't figure out the causality of that. So there are some ideas around that that the Open Modelica people looked at for debugging. I would investigate that, but it's challenging. It's a tricky thing, especially if somebody comes from the Simulink background, because they're used to think it's very imperative in that case, and it's very easy to trace where the stuff comes from. So Chris, yeah.
What is the one feature or domain that Modelica did not do that it should have? Is it, jump, stochasticity, or is it more like, a domain like it should have gone into chemical reactions more? Like what is like the one thing that's like, oh, I really wish it did that?
Well, I mean, one answer would be something like PDEs. It didn't bring that sort of expressiveness to the PDE world. I don't know what the demand is in the PDE world, but that was my PhD work was actually in something very similar. So that would be one answer. I'd say that we pushed fluid modeling pretty far in the Modelica space, but I think that the future of that endeavor is still up in the air. I think there's still plenty of room for improvement there. So that's the multi-body systems and fluid systems, especially two-phase or multi-phase fluid systems, are really tricky to do in terms of user interface, in terms of diagnostics, in terms of just numerics and initialization. So everything, electric circuits and stuff, that's pretty well established. And even just simple mechanical systems are pretty straightforward. But those are the two frontiers where I feel like it always gets kind of dicey. So.
I can comment on that. Well, the thermal stuff, you even have companies that only work on thermal modeling in Modelica.
Yeah.
Therefore, it's hard to tackle that field from my point of view.
Hmm. Yeah. Anyway,
but that's due to business reasons, not due to technical reasons.
Yeah,
I agree with you in technical reasons.
Yeah, one answer, Chris. I did something. I did a paper once on economic modeling. Modeling sort of supply and demand kinds of things. That was pretty challenging to do in Modelica. Not because of the math, but because just the way the user interfaces and the GUIs and stuff are set up. It just wasn't really well suited.
So. A last quick question.
Thanks for a very insightful presentation. So just to tease a little bit, what do you think the open source can bring to Julia that didn't bring to Modelica?
Well, I mean, just to be clear, Modelica's specification is open source, its standard library is open source, and there's an open source implementation of Modelica called Open Modelica. So it's not that there's any lack of open source in the Modelica community. I think I would say that what Julia potentially could have as an advantage is taking the more Pythonic sort of approach, in that you have essentially a standard implementation of, say, for example, ModelingToolkit or something like that everybody builds on, instead of every company who wants to be involved in this space has to build their own. They can just build on top of that and provide content on top of that, model libraries on top of that potentially. So that's where I think the open source part would be the biggest advantage, is just having a single starting implementation.